Well, good afternoon, ladies and gentlemen. I'm Dave Deptula, Dean of the Mitchell Institute for Aerospace Studies, and welcome today to the Mitchell Institute's rollout for our latest research study, Digital Engineering, Accelerating the Development and Delivery of Defense Capabilities. Now, today, the Department of the Air Force, and really the entire Department of Defense, faces a critical moment in its efforts to modernize its force to meet the demands of strategic competition. Chronic capacity and capability shortfalls, coupled with the blistering pace of China's military modernization, highlight the urgent need to transform just how we develop new weapon systems and capabilities. Traditional acquisition processes are struggling to keep up with these growing demands. Lengthy development times are increasingly unsustainable in an era of great power competition. To address these challenges, the military services are increasingly turning to digital engineering, leveraging advances in computing power, modeling, and simulation, as well as data analytics to revolutionize the acquisition, production, and sustainment processes. So with that bit of very small introduction, let me turn this over to Heather Penney, the report author, to provide you an overview of her research. So Heather, thanks for being here, and over to you.
Thank you, sir. If we can get the slides up, please. And thank you everyone for joining us today. When Brian Morra, my co-author, when we first embarked on this project, we realized that even with all of the hype and the excitement surrounding digital engineering, there didn't appear to be a sufficient understanding of what it was, its potential benefits, its limitations, its cost, and there also didn't appear to be a real depth or nuance of understanding that could support smart policymaking. So when we initially took on the project, we thought it would simply be a primer on what is digital engineering. But what happened is, as we were talking with engineers and program managers, we realized that digital engineering has the potential to accelerate defense capability development and fielding without the need for acquisition reform. And this could have a major impact on our strategic positioning against China and Russia. Because as we are, as Secretary Kendall said, out of time. You've heard us say this before, that the US Air Force is the smallest, the oldest, and the least ready that it's ever been in its history. China is outpacing US development and fielding of advanced weapon systems, and they're building a lot of them. Already they have 200 J-20s, and they're building more at a rate of 100 a year. Compare that to Air Force recapitalization rates. And of course, we could discuss the role that the budget plays in this. We at Mitchell have done a lot of budgetary analysis on why the Department of the Air Force is in this position and what we should do about it. After decades of underfunding, the Department of the Air Force faces a major crisis in recapitalization across all of its major weapon systems. The department needs more resources, make no mistake about it, but it also needs time. It's not just about money. On the right hand of the slide, you can see a list of common persistent problems that RAND found with the DoD acquisition programs. All of these issues slow down capability development and delivery and increase cost, a double whammy. It takes decades to go from capability gap analysis to fielding. And even if there were unlimited budgets available, and they're not, the Department of the Air Force cannot buy time. China's not waiting, and we don't have the time to lose. So we know that we need to go faster. DAF leadership recognizes this, and that's why we've seen so many innovation offices sprout up around the Air Force. The Air Force's Rapid Capabilities Office, or RCO, was stood up in 2003. And while many RCO directors will say that they are subject to the Defense Federal Acquisition Regulations just like any other acquisition professional, and they are, the difference is that the RCO also has a tremendous advantage in that they have unique authorities. On their homepage, on the RCO homepage, they actually say that the office preserves the strength of US ingenuity and innovation without the rigidity of traditional acquisition. That's saying a lot. So the Air Force's RCO, the Space Rapid Capability Office, and even OSD SCO, they're important organizations that focus on a small number of often highly classified capabilities. So these offices go fast and deliver good stuff, but their organizations and their approach simply cannot scale. Consider all of the programs that the Air Force has in its portfolio and its recapitalization needs. So RCO offices are small and focused so that they can be flexible and fast. The fact is, normal contracting offices cannot replicate RCO processes. So the DAF has tried to open their system to speed and disruption through innovation offices and challenges like AFWorks or Spark Tanks. But these also have struggled to scale. Again, they're doing good work, but they're simply not designed for major defense acquisition programs like CCA, NGAD, or NGAP, for example. So these innovation offices might work for small, inexpensive things, but not major capabilities or programs. We cannot transform the DAF through these innovation offices, but we can't do it through normal acquisition processes either. So this puts the Department of the Air Force in a lose-lose situation. Clearly, something needs to change. Digital engineering has the potential to address and resolve many of these issues without acquisition reform. This is a potential game changer for the department. Look, acquisition reform is noble and worthwhile work, and we must continue to invest in reforming the acquisition system. And we need to resource the Department of the Air Force. This means both the Space Force and the Air Force. We've got to resource them so that they can fulfill the concurrent demands of the COCOMs and the expectations and needs of a greater conflict. But one thing we can do to move faster and with greater impact is implement digital engineering across the entire DAF. Digital engineering could accelerate and improve capability development from the very beginning of requirements analysis and trade-off studies through design and testing and on to production and sustainment. There's goodness here across the entire life cycle of the weapon system. Digital engineering can move the needle in our strategic competition against China. So, what is digital engineering? It takes advantage of advances in modern IT infrastructure like high-speed, high-bandwidth secure networking, big data processing, and cloud computing and storage to create a digital library of models, data, documentation, and other artifacts, which allow engineers, developers, program managers, all stakeholders to access and share information in real time about any and all aspects of the program. So this empowers stakeholders to operate from a single, centralized and authoritative and synchronized database. And this reduces friction, rework, and it increases transparency and oversight for everyone. Okay, I said a lot of stuff. Let's unpack that because it's a lot of jargon and words. What does it really mean? We're going to go through a little history trip here because I think that going through the history of how digital engineering evolved can be helpful in understanding the power of where digital engineering stands today. So the first evolution into today's world had to do with the development of systems engineering. In the 1950s, aircraft were becoming more sophisticated and complex than they were in World War II. As technology began to accelerate into the Cold War, aircraft increasingly relied upon the development of specific and exquisite systems to achieve designated performance requirements. And the complexity of these new weapon systems required a different approach that treated the aircraft as a holistic system, not just a flying machine with pieces and parts. But still, disconnects and friction would occur because remember, computation was still very nascent and it relied upon manual paper designs and calculations. And this desynchronized teams and really created challenges when it came to version control. And this drove time into program development. So advances in computation and modeling in the 1970s through the 90s provided engineers with more powerful tools with which they could design weapon systems. CAD, CAM, so computer-aided design, computer-aided modeling, these are things, but these models still lived on a single hard drive or a drive within a local area network. So programs still had to use paper versions to share information across teams. So you can think about this phase of systems engineering as being digitized. Engineering work remains fundamentally unchanged from an analog era. It's just better because engineers are using computer-aided design tools, but they still dominantly rely upon paper artifacts between the teams because the software tools don't enable collaboration and certainly not synchronization. So all of that friction within the program management still exists. Model-based systems engineering developed in the 1990s, and this elevated a digital model over the paper artifact as the primary reference point. This engineering approach did a lot to get teams on the same page, so to speak, and to leverage digital models throughout the program's lifecycle. Model-based systems engineering also began to shift program management through an emphasis on digital tools. But again, these models could not be shared easily, so processes remained siloed, and design reviews, approvals, they remained paper-based, linear, and dependent on the previous milestone. What knits all of this together today, and frankly, transforms all of these previous developments, are the advances in big data processing and storage, cloud computing, and high-speed, high-bandwidth networks. This is the glue that enables teams and engineers from different companies and continents, program managers, government oversights, any stakeholder in the system is now connected, and they have insight to any facet of the program. And all of this happens in real time. So for those of us who are not part of a digital engineering team and haven't experienced this firsthand, we can think of it like editing a document on Google Sheets, Google Docs, or something in Microsoft Teams. We can designate who has access and editing rights. And because the file is located in the cloud, anyone can edit at any time. There's no version or configuration issues. And you can see real time when someone is making changes, and all those changes are tracked for review and approval. So now with this digital thread, program reviews from the management side can be continuous, real time, cross-team, and on demand. This connectivity and insight into the program's artifacts can empower program managers, enhance and expand their knowledge of the program and its design, and accelerate executive oversight and approvals. This is how we speed it up. Digital tools and program management practices can be radically transformed by this kind of connectivity, cloud storage, and computational power. This is the power of the digital thread. The key is we have to choose to use it. Okay, so before we go too far, we're going to cover some basic and important terminology related to digital engineering. I'm not going to read the slide to you. You can see some of those highlighted parts, but I do want to point out two really important terms to highlight and the differences between them: a digital model and a digital twin. There can be a lot of confusion on these two terms. They're both models of the system, but the main difference is that the digital model is a notional model of the generic system. A digital twin, on the other hand, is an identical copy of a specific system. It's avatar, right, of that specific thing. So to be accurate, the digital twin must be continuously updated with the real world experiences of its real world article if it's going to be accurate. So for example, a program office might maintain a digital model of, let's say, a next generation cargo aircraft. Every individual tail number, though, would have its own individual digital twin. So these twin models would be updated with the flight set times, cycles, loads, maintenance, fuel, et cetera, that their specific tail number experienced in the real physical world. And these events and stressors could then inform predictive maintenance for their particular tail, or you could take all of the data across the twins and aggregate them to update the type's digital model. So digital models are good for system design, fleet management, service life extensions, modernization, but use cases for digital twins are really more focused on specific maintenance and management actions. It's also important to note that digital engineering is not a one-size-fits-all, and getting the most out of it is going to require judicious and risk-balanced implementation. So we've got to be smart about it, especially because for the Department of the Air Force, we don't have all new things. The vast majority of the Department of the Air Force's force structure is really legacy. Now, when we look at New START programs, they can maximize the benefits of digital engineering by using it from the very beginning. So programs like B-21 or NGAD, they've been using digital engineering principles during the requirements and design process, and they're applying these technologies through the testing and production in the planning for sustainment. So New STARTs are the types of opportunities where it's obvious from an engineering standpoint to implement digital engineering. But are we really maximizing the program management potential of these New STARTs? Are we doing the continuous reviews and oversight that we can use to accelerate their delivery and fielding? Or are we forcing these programs to still do business the old way? And this is an important point because digital engineering is not just about the engineering tasks. We need program management on the government side to embrace the digital engineering management principles and technologies if we're really going to maximize the potential to deliver the speed and quality that competition against China demands. Now, older defense platforms can also gain advantages from prudent application of digital upgrades, depending on their level of age and the program's use of digitized software and modeling. So true legacy programs like the B-52 that wasn't designed with anything digital, these can benefit if we appropriately scope those efforts. So for example, reverse engineering a digital model of the B-52 wings could be very useful for their re-engineering efforts. Hybrid programs that have some level of computer-aided design and modeling may also be able to leverage that for part sustainment or remanufacture or diminished manufacturing sources, but it probably doesn't make sense to try to recreate digital twins for the entire legacy fleet. But bottom line, for any of these programs, new or old, data rights is also going to be a consideration that the department and companies need to be aware of, because data is king in digital engineering. So speed, cost, and quality. These are all ways, and by the way, the list that you see on this slide is not exhausted, that we found that digital engineering, when implemented to its full potential, can improve system design, development, and delivery. And again, all without acquisition reform. But this is primarily applicable to new starts. This is when we most fully realize these benefits. So programs like Sentinel, B-21, Next Generation Air Dominance, any of the collaborative combat aircraft, these are best positioned to realize the full suite of advantages that digital engineering can offer. Again, it doesn't mean that digital engineering is only relevant to new start programs. Legacy and hybrid weapon systems also stand to benefit from digital engineering. And many of these advantages are related to the challenges that these types of weapon systems face in ongoing sustainment and lifecycle support. Again, things like diminishing manufacturing sources, dwindling supply bases, or service life extension programs. The scope of these activities could be minor or major, and core to any would be obtaining the data rights and establishing a digital baseline. If a company is unwilling to share their data or provide rights to the DAF, the department may be forced to reverse engineer a digital model of either the entire system or the adjacent systems before they embark on these kinds of sustainment or modernization activities. And this is not quick or cheap. For example, it'll take an Air Force team well over 6 years to create a digital twin of a single B-1. So senior leaders really should understand the purpose and the costs of these kinds of activities and how developing these models will benefit their sustainment objectives. The point here is that program leadership must have that kind of clarity of their objectives for the effort and why. And this will help them scope their digital efforts to maximize benefit and control costs and schedule. So our research found that there are also some significant barriers that the Department of the Air Force faces in unlocking the full potential of digital engineering, whether or not that's for a new start or a legacy or a hybrid program. First, we've already spoken to the need for program leadership to understand their objectives for implementing digital engineering, especially with those hybrid and legacy programs. And this is because reconstructing digital engineering models and other artifacts will require significant effort or have substantial technical debt. Technical debt is the engineering work that must be accomplished before one can move forward. And this is particularly relevant to the Department of the Air Force because so many of our weapon systems are decades old. Which leads to the second challenge, that the costs and financial benefits of implementing digital engineering are not well understood by the department. Some companies are tracking their digital engineering work and comparing their cost and schedule outcomes against historical estimates using analog efforts. That is, what the project would have required if they didn't implement digital approaches. So some companies are actually capturing that business case analysis, but the department itself does not have robust data on which they can understand when and how much digital engineering to use on their programs. So they lack the data to really understand the business case for how to scope their digital efforts. And part of this problem is related to how deeply companies can push digital engineering into their supply chain. Nearly every prime or large defense company has implemented some degree of digital engineering, and some more than others, and some, better than others. Quality here matters as well. But the sub-tier suppliers can be a wholly other matter. Here, small supply shops may lack digital software tools or the training to use them, or the infrastructure, the IT infrastructure to use them. And those digital modeling tools might also be incompatible with their in-house software machines or other production tools. But by and far, the largest and most significant barrier to adoption that we found was the cultural resistance and lack of expertise across the Department of the Air Force workforce. This is really important. There are definitely pockets of excellence within the department that are using digital engineering to engineer, but the areas that need the training and incentives to use digital engineering are actually in the acquisition and program management career fields. We need to understand, these professionals, acquisition professionals, are monitored, rewarded, and punished by how well they execute to their processes. And in this context, using digital engineering to accomplish the same tasks and functions, but in different ways, could incur risk. So the department needs to provide the necessary training, guidance, and practices for these professionals to follow. By providing their acquisition and program management professionals the training that they need to understand and apply digital engineering management practices, the department could begin to unlock the full benefits of digital engineering across all of its programs, from legacy to new start, and really be able to get to that speed and cost savings. So our recommendations, fundamentally, the Air Force needs to incentivize the use of comprehensive digital engineering for these new start programs. This is really going to be a sweet spot, and it's going to be crucial to transform the force into a force that can really deter and prevail against China. Leaders also need to assess the feasibility of digital engineering solutions for legacy and hybrid weapon systems. They need to be able to understand the scope of work that should be applied, as well as the business case. Importantly, they have to train their acquisition workforce to use digital tools and processes. This will be key to unlocking that speed that digital can offer. And they must be able to promote open standards for digital engineering tools. This is kind of creepy, but this gets to the point of really being able to allow digital tools to be used across all of the primes and across all of the sub-tier suppliers. And to this point, the department should also consider maintaining a library of digital engineering tools that are accessible to these smaller businesses, sub-tier suppliers, or other non-traditional companies that have not invested in building up their own digital tools or acquiring their own digital tools. And finally, for any of this to work, it relies on the backbone of the IT infrastructure, the network. So the department and its prime contractors, partners, and suppliers, we must ensure that their IT infrastructure is modernized and secure, because digital engineering can restore the speed of capability development, acquisition, and fielding that we need to be able to outpace China. Thank you. Sir, back over to you.
Well, thanks very much, Heather. Really appreciate that presentation and all the hard work that you put into it. Now, what we've got planned here is to further discuss digital engineering. We've gathered a distinguished panel of leaders from the Department of Defense as well as industry. So let me take just a short minute to introduce these individuals, and then I want to give them a short period of time to give us their perspectives, and then we'll jump into questions and answers. First, we're happy to be joined by Dave Tremper, the Deputy Assistant Secretary of Defense for Acquisition Integration and Interoperability. Thanks for being here, Dave. Then we have Mr. Drake Harris, the Director of Integrated Systems Strategy and Business Development for Lockheed Martin's Advanced Development Programs, otherwise known as the Skunk Works. Thanks, Drake. And finally, we're glad to have Jeff Reed from Northrop Grumman, where he's the Director for Engineering Digital Transformation and doing some great work there. So thank you, Jeff. So with that, Drake, over to you.
It's a pleasure to be here today to discuss digital engineering. It has been such an impactful disruptor to the defense enterprise, and I think it has remarkable capability. Heather's policy paper, if you've had a chance to read it, then you know what I'm talking about. If you haven't, I encourage you to do so. It does an excellent job of capturing the key tenets of digital engineering, both the benefits, as Heather described, and also where the challenges lie. One of those things Heather highlighted was IT infrastructure. That is critical, both in industry whether in the primes or in the supply base or at government. I've heard other general officers on many occasions saying, okay, their problem now, their fight is in the IT realm to equip for that. Digital engineering is such a key enabler, though, for it. But one of the key things to me that its benefit is it enables collaboration and transparency and partnership. As Heather said, how do you move faster? Those things now allow you to move faster. If we over communicate, so to speak, in the engineering and the acquisition world, then we can pick up the pace. This is such a rich field and an exciting path forward, and I believe a game changer. This is truly disruptive. Over to you.
Okay, sounds good. Jeff, let's shift to you while Dave's working on his problem there.
Okay, thank you, sir. And Drake, well said. I will say that, Heather, congrats on a well-written paper. I've read it a couple of times now. I think you've hit well on and you've described the challenges and opportunities that we see with digital engineering as we implement across the programs. And I will say that I think many within the A&D industry don't fully understand some of the complexities as well as new challenges that digital engineering is bringing to us. I like that you've highlighted opportunities that digital engineering provides across the entire product lifecycle. You're addressing areas that aren't always considered, like meaning real benefits that we find throughout and further down the life cycle. Manufacturing, sustainment. That sustainment, I can tell you from experience, is not often touched upon unless you got a maintainer in the room who's experienced needing as designed information, analysis that builds up a product, information to perform a repair for a fielded asset, for example. And I like also that you and Drake also just touched on the IT infrastructure, that having that right infrastructure enables us to connect digital engineering from the initial requirements all the way through sustainment. And for Northrop Grumman, right, our digital engineering implementation is beyond engineering. So I like the definitions that you state. It starts in program management, business management, manufacturing, logistics organization, as well as all of the disciplines within engineering. Our digital transformation as a whole is not something we're doing program by program. It's a full enterprise-wide effort where we're taking capabilities developed on one program, we're applying lessons learned, and we're scaling for all programs. So all of this is being done on a common IT infrastructure that enables collaboration across the disciplines and across the functions. So we've been using digital engineering models for decades, but what's different today is the technology is enabling us the ability to link designs across the product lifecycle and establish that digital thread, enable reuse of models across the lifecycle by previously siloed organizations, and finding and correcting inefficiencies early on through virtual tests, through virtual buildup of the product, your virtual model that you described. And we can do all of this before initial engineering release. So think about the acceleration and maturation of our product development as we work through EMD phases. And I will say one more piece here is that if you think about what that brings to speed of delivery, when an engineering error is found, the impacts that can occur. If we find on the factory floor, even when you get a quick fix developed by a liaison engineer, it's still slowing down the production process. But if you find these types of errors further on down the life cycle, such as during flight test, the rework, the redesign that can be extensive and have a significant impact on our schedules. So digital engineering enables us to find those, again, prior to initial engineering release, which is where we see the primary benefit. Thank you.
Oh, thanks for that, Jeff.
So first thing, I wanted to compliment Heather on the paper. Very well written, and when I read through it and I was thinking about it in the context of my considerations when it comes to the acquisition side, as I thought of things, it was almost like I would read it in your report. So I think you covered down on a lot of the challenges that I see on the acquisition side. Some of the huge advantages I see for digital engineering for the kind of long and clunky acquisition processes is that it allows us to parallelize a whole bunch of traditionally sequential processes. So if you look at things from basic S&T all the way through prototyping, through integration, transition, acquisition, and sustainment, we typically think about that entire process as a sequential process, right? First, I have to do designs, then I got to build test articles, then I got to build a prototype, then I got to do some developmental tests, then I got to work some integration problems, then I got to do certifications and approvals, and then acquisition, and then all the sustainment stuff. And when you map out the timeline associated with each one of those steps, you end up with 15 to 20 year long processes. So my new office in ANS was set up specifically to get at how do you accelerate capability delivery using existing acquisition authorities, or not even just acquisition authorities, but existing authorities. And I'm going to use that word integration, and you used it a few times too. And that word integration is extraordinarily important because we tend to speak about the I word innovation without speaking about the word integration. And what we end up with is we talk about innovation stalling at the valley of death, okay? And we look at the valley of death, and we kind of go down and we explore the rusted out hulks of old technologies that showed up in the valley of death. And what you find is that a lot of things died because nobody would step up for the integration piece of this. And that's things like the certifications, the approvals, the flight worthiness, all of this more blue collar engineering type of work that you have to do after you've demonstrated a technology at TRL 7. And that TRL 7 term becomes important too. And you highlighted it in your opening remarks. Optimistic TRL. Optimistic TRL can cause a big communication breakdown between the S&T community and the acquisition community. When you start to play in these digital engineering tools and you start to allow yourself to parallelize the processes, now you can have the acquisition and integration conversations going on at the same time that the technology is being designed and developed. Now I don't have to wait for the test articles. I don't have to have those first units coming off of the line so that I can then decide whether I want to certify and approve it, and whether or not the anti-tamper is sufficient to support an operational deployment of that system. That breakdown of those traditional sequential processes, which can take that 15 to 20 years, suddenly converges down into more of that 5 to 10 year time frame, where now I can take a prototype that I've initially designed as a production level prototype, and I can work at the certification and approval processes and the risk reduction processes in parallel with the actual hardware development, right? So as I'm building out that prototype, I can actually work the certification processes. So within ANS, we're looking at all of those convergence opportunities, and it's things like the adaptive acquisition framework. And you mentioned it in the report. The adaptive acquisition framework is extraordinarily important because it provides flexibility to acquisition program managers. It doesn't dictate how you do acquisition, but it provides tools like the use of a rapid prototyping pathway. If I've got the access to a prototype unit, I can accelerate an acquisition program post milestone B, potentially even post milestone C. Why that's important is that term rapid prototyping shows up in the S&T community too. And in the S&T community, there's year of execution discretion on the initiation of a prototype, right? There's a rapid prototyping program that R&E has that allows them to start building a prototype the year that they decide that that's important, or designing a prototype. What that means for acquisition is that if I can converge those prototyping authorities between S&T and acquisition, I can effectively start a program of record tomorrow if I have tight alignment between the S&T community and their rapid prototyping efforts and the acquisition community and their rapid prototyping portions of a middle tier of acquisition program. So there's acquisition authorities that are in place that allow us now to start moving fast. When you converge that with digital engineering, now I can start working the integration processes fast. So as the S&T community is building their prototype, I can work the certs, accreditations, and approval processes. I can work the testing plans. We can have all of those things going on in parallel, and no longer then are we stuck to this sequential order of acquisition that forces us to have a product level ready before I can engage the next part of that process. So I applaud you on the paper. I think what you've laid out in the digital engineering study highlights all of the challenges, but also the opportunity space that exists there. And when you marry that up with some of the rapid acquisition tools that we're attempting to give program managers, I think there's a match made in heaven.
Well, thanks very much for that, Dave. Don't touch anything. We'll just keep you live here for the questions. The first one, let me throw out, as you talked about just a little bit or alluded to, the department's made digital engineering a priority in recent years, and industry's been doing the same. It's really an incredible alignment, which kind of begs the question, just what are the key factors driving the adoption of digital engineering processes across the defense acquisition enterprise? Again, anybody can jump in there.
So I'm happy to take a first stab at that since my microphone is working. I think obviously it's the end product, right? It's the ability to go fast. And if I have this digital engineering infrastructure and the tools and the workforce in place to do digital engineering, well, now it allows me to go fast. I can parallelize all of these processes. I can do things quickly. I can also do things like take a subsystem that's used in one system and translate that model over to another system and see what's the impact if I reuse that investment, the investment in the model and the investment in the actual technology. What's the impact in this other operational space, this other domain? So from a joint integration perspective that I'm looking at, I want to be able to understand, can I take a system that the Navy built to go after a Navy specific threat and move that system and use it in an Army operation, right? What are the integration implications of taking that Navy system and putting it in that Army domain? Is the threat common? If the threat is not common, but the function is common, what's the implication? What's the modifications and tweaking that I would need to do to that Navy system to facilitate the migration to another services application? Digital engineering provides profound value in the ability to do something like that, to start looking at those cases, understanding the edge cases, understanding the integration needs, and start laying out what are the requirements that I would need to have, what are the resourcing that I would need to have to actually make that potential operational capability a reality.
Very good. Jeff, Drake?
Oh, go ahead, David. Go ahead, Drake.
Forgive me, Jeff. I appreciate Mr. Tremper's comments. They're spot on, of course. You know, the devil's in the details, and what digital engineering, I think, or I could even say some in the department are starting to use the word digital material management, which I think is also a good way to think about it. It's more than just the engineering data. It's the system engineering, it's the requirements, but it's also, the program management data, the financial data, the production data, of course. Jeff, you talked about it earlier, the sustainment or logistics data. All those things being within one tool, those are, if you can manage at that detail level, then you can start making the vision that Mr. Tremper laid out, where you can move quickly through all sorts of different domains, translating capabilities from one place to the other. All those things are then becoming enablers. Jeff, I stepped on you. Other thoughts?
No, just to add on to what Mr. Tremper was saying, I really like the reuse comment that you made, right? Being able to reuse systems. If we think about, and there are barriers that come with that, but if we think about reusing models throughout the product lifecycle, we see tremendous benefit. And I think within that program, we can see tremendous benefit. With what you mentioned in reusing across programs, there are barriers that we need to come and obstacles that we need to overcome. Classification levels, being able to see that information from program to program are fundamental barriers that we do need to overcome. But we've talked about this. I've talked about this with customers on how we overcome that. But you are spot on when you say that the digital engineering capabilities are just teeing us up for really getting some efficiency from being able to reuse, again, not only within the program across the product lifecycle, but now starting to go across programs. And the only other thing that I would add is that having an infrastructure that enables that is so important. We touched on the IT infrastructure and being able to now leverage the lessons learned as we apply digital engineering across multiple programs. At Northrop, we're not doing that. I mentioned we're not doing that program by program, but we're bringing that to that common environment where we've got now over 140 programs that are operating on the same infrastructure and gaining lessons learned from some of the major programs that you mentioned, Heather mentioned in her paper and on our slides earlier today. So the benefit is just incredible and unleashing capability, I think, that we've not seen before.
Thanks, Jeff. Now, shifting to digital engineering processes does require substantial change in mindset and skills, especially when it comes to the acquisition and engineering workforce. So what steps are you all taking to train people to make the most of the digital engineering processes and tools? Anybody?
I guess I can start, and I'll just probably a quick answer to this. It is a cultural transformation, right? We've got, if you think about it, we've got experienced engineers that are changing how they think and work as we introduce digital engineering. We've got new engineers that are demanding the newest technology, and the training that we provide is evolving. I can tell from experience, we've got engineers that do not want to sit through a 40-hour class learning buttonology on a new tool, for example. They want to be able to look at YouTube type learning for task oriented. I've got a specific task that I need to go and work through, and we're developing those and we're sharing those in our infrastructure to share best practices from program to program. So it could be a 2-minute video on how to implement something into one of my models versus going to a class, learning how to use the tool. And then by the time you actually need it, you're probably forgetting or stumbling through how to use the tool. So it's a little bit of a different mindset that we've experienced as we start thinking more about training the entire workforce.
I agree with Jeff. I think, it certainly is culture isn't such an important part of becoming digitally transformed, past tense. At the Skunk Works, we have over 50%, I believe, of our workforce at the Skunk Works right now is our new hires are younger, even Gen Z or things of that nature, where tech is already such an integral part of their lives. But what we're finding on our new programs, certainly as we start them in the digital engineering, the digital material management type environment, that I'm sure Jeff has found the same. Also, that even our experienced designers, engineers, and folks are able to readily embrace that when they see, oh, this makes my job easier, not harder. And if I take this little bit different approach, here's all the benefits to even what I do as an individual. And I think that's a key thing. It's such a cultural thing, but we have found, and I think the rest of our industry will find, not a gigantic resistance to that, especially when they see, oh, this makes everything easier.
And
I'd like to
I'll
jump
add
in
from the DoD side that as you can imagine, the acquisition processes and policies within the department, there's a lot of old dogs that are in that process and who know the process backwards and forwards. So you can't just snap your fingers and say, hey, everybody, we're going to go to this world of digital engineering. Let's all get in line, because there's processes and policies that have evolved over many years that people are satisfied with in some campaigns, but unsatisfied with in other campaigns. I think what the department has been doing is we have something called the Defense Acquisition University, and that DAU is what's used effectively to train the acquisition workforce, right? You have certification requirements, program manager requirements, advanced PM requirements associated with the Defense Acquisition University, and you have courses. It's not just sitting down for 45 minutes and watching a PowerPoint slide deck. It's a 6-month course, right? Some are in person, some are online. There's testing required, credentialing associated with that. The department has stood up something called the Digital Engineering Credential. Right? And the Digital Engineering Credential is a series of courses. It's 5 courses mixed in with some webinars that allow learning on new model development. How do you use digital engineering and acquisition programs? And that credential has been given out. There's 1,200, I think, folks that have come through that credentialing process since that course was stood up in 2019, and it's continuing to evolve. So we're using that Defense Acquisition University pathway to get at the acquisition workforce with the training. The other thing that offers is a virtual environment for digital engineering, where you can actually, the students can go into a simulated environment where they would use digital engineering tools and learn how to apply the different models and the different tools within that domain, so that they can understand the significance of digital engineering. R&E has created something called the Digital Engineering Workforce Plan. It was a response to a FY20 NDAA direction to the department to come up with how are you going to do digital engineering training. So that exists, and it lays out the strategies, which include things like this accreditation course that goes along with it. But there is an active campaign within the department to put those training courses in place, so that the defense acquisition workforce is required to go through those training as part of their credentialing for acquisition program management.
Well, thanks for that, Dave. Now, I do want to save some time for our audience. So I got one more. Appreciate y'all. Give me a quick answer to this one, and then we'll shift to to the audience, but it can be tempting to think of something as a panacea that will fix everything. And it seems clear that digital engineering has a lot of benefits, but how do we know? So for our industry partners, have you been tracking your digital engineering programs as compared to traditional programs? And do you have any quantitative evidence that you can share with us on this subject?
I could start. I think that's a great question. The first things our program managers, our CFOs ask us is, okay, we're going through the cost of implementing digital engineering. You want to bring these new tools in. How can I now reduce my BOEs? And it takes time to be able to do that, right? To do that in a valid manner, if you will. But we do have examples. I mentioned that our foundational infrastructure that enables collaboration between employees, customers, and partners. Well, we've established that for a single program. We built it and now have over 140 programs in use today that enable us to quickly set up a program and get them using the tools and gaining the efficiencies from lessons learned on previous programs. So that's one piece. And then the other piece that we're doing, and I'm going to say we're doing it in pockets, and it's a little bit of looking in the rearview mirror, but it's the best way to justify that we've got a real ROI. One example is where we've implemented model checking. In other words, prior to our engineering release of models, we're going through some automated model check-ins, checking for producibility, checking for typical design errors that could occur, that could just be missed by the designers. And we are looking back. We know what our rework rates are on previous programs, and we're comparing them and looking at a real program, a large program, one of which was mentioned in the paper, where we are starting to see our compared rework rates are going down. And that's something that we can start building into the next program using those same processes with confidence that we'll be able to achieve it.
As Jeff said, I guess I often say too, we're all slaves to our database. Certainly when you're looking at BOEs and looking at historicals, and then, so what's the payoff? What's the benefit? At the Skunk Works, we've had the opportunity with a few projects that we've done to do an is-was type comparison, where a particular system was built using what I'd call, for the sake of this forum, traditional methods, so to speak. And then re-engineering, taking part of that, re-engineering it with digital processes, all the way from engineering requirements through supplier management, through shop floor instructions and manufacturing, and looking at those and doing them again, and then comparing the data. On the first article, this was our results in terms of hours required to build the article, rework, and so forth. And we found a dramatic decrease, both in the hours, in a completely apples to apples comparison, both in the hours to manufacture. But in Jeff alluded to it as well. He's spot on. We also found what we thought was a surprising decrease in rework, because of digital engineering, when you move the learning process, the discovery process, to the left, and you do it earlier, all that stuff gets done before you have to have learning on the manufacturing floor. That data has been pretty compelling.
Okay, very good. Thank you all for that discussion. Like I said, we're now going to open the session to questions from the audience. So I think all of you know the drill by now. When I call on you, please state your name, and then, first open your mic, and then you state your name and ask your question. And I've been anticipating throwing the first question here to my good and old friend, Neil Cassina. So Stub, you got it.
Thank you. I just wanted to note that it seems like all the digital engineering you're talking about is a super valuable tool that is developing right before our eyes, but it really targets the achievement of trust is the big picture. And, as Drake noted in his 3 tenets, that really go all the way back to Kelly Johnson. I won't repeat them, but developing an environment of steady state trust in program management is the essential goal here. And there's nothing that really does that by the transparency, if you will, the collaboration, the other elements that come out of a digital engineering, of everybody having the same picture, having it in real time, being able to focus on the real issues and not having to just spend hours and hours of program management reviews and just getting everybody on the same sheet of music, seeing what the current status is. So you've said all that. I'm sorry, but I just wanted to focus it on trust. Thanks.
Hey, good point, Stubb, and glad to see you're still kicking and representing the F-15C weapons school community very well, because there are too few of us still left. Okay.
We missed you at the 75th anniversary, by the way, Zatar.
Yeah, no, I was in Kyiv in Ukraine offering my perspectives on how they can do a better job kicking the Russians' ass, but that's another story.
Good on you.
Let's talk to see what Brian Morra, who's Heather's co-author, and Brian asks, my question is, what do our panelists see as the #1 hurdle in implementing digital engineering in government and industry, respectively?
You know, if I could leap in ahead, I'm sure Mr. Tremper has comments as well. One of the leaders in the Air Force has said, for one thing to change, everything has to change. And I think that's key. This digital engineering is a journey for all of the defense enterprise. And if only one element is on that journey, then it's not going to work. Everybody has to join in. Mr. Tremper, I think that's exactly what you said earlier.
Yeah, Drake, you nailed it. So this is an enterprise level need, right? And so as an enterprise level need, there's an upfront infrastructure resourcing need, training need that then filters down to the workforce that effectively aligns it and enables it. And that's a big hill to climb up front. And so who climbs the hill? Do you ask independent acquisition programs to climb the hill in their own stovepipe, or do you try to address this from an enterprise level? There is a DODI now out for digital engineering that says that digital engineering is a requirement, or it's directed for use in acquisition strategy. So you at least have to accommodate the use of digital engineering in your acquisition programs, but now you have to align it. And if the Air Force is going to do it one way and the Navy is going to do it another way and the Army is going to do it a different way, how do you converge that alignment? And what we've seen happening in some of the digital engineering movements of the service components is that there's a functional mismatch between the way that they're decomposing digital engineering into their respective services. If you try to then converge that on the joint side, you run into this integration and interoperability problem in that digital engineering space because they aren't inherently compatible, their digital engineering pathways. So I think this is where ANS and R&E contribution, the OSD, ANS, and R&E, the fourth estate of the department, that getting into that enterprise level tools, understanding what the Air Force has, picking that up, propping it up, and making an enterprise level resource to the rest of the department. I think that's going to be extraordinarily important in how we migrate through that disconnected service components use of digital engineering.
I'd like to bring up something that that we haven't really addressed either in the briefing or in the discussion thus far, and that's the notion of test. So whether or not that's developmental test or operational test, we need to ensure that the testing community is integrated into the digital engineering enterprise, because there are so many areas where we can model that and achieve the test points, validate the test points, do some discovery that the test community would traditionally do in live fly or through other physical testing means. And so while I think there's always going to be a need for edge cases to be tested, I think that that's a piece that we want to ensure gets included within the transform it all, because we can't be disconnected from that. Otherwise, the testing will really drag things back.
Okay, here's one. I normally don't ask questions from anonymous attendees, but this is a pretty good one. Large OEMs like Northrop and Lockheed are at the leading edge of digital engineering capabilities. The Department of Defense is less equipped to evolve rapidly and in line with emerging technologies. How can we bridge the gap between what OEMs/industry are capable of delivering and what the Department of Defense is capable of acquiring, integrating, and managing effectively. And Dave, I'll give you the first shot at that.
So I think key to this is are those interface levels, right, between the system. When you break down a system into its particular components, its major functional areas, those interfaces are extraordinarily important for enabling access to non-traditional companies, to third-party developers in support of prime system development. So when we get after the digital engineering aspect of that, being able to model the third-party insertion of subsystems and components into that system are part and parcel important to owning those interfaces, right? And so this gets into the conversation about data rights. Well, what are the data rights? Who owns the interfaces? What's the appropriate level to create the interfaces that allow for those third-party accesses? I think that's true both in traditional acquisition development, in the application of modular open system architectures to our system design, which we've been doing for the past 10 to 15 years. And it also migrates its way into this digital engineering space so that we can also bring in those third-party models through those open APIs and those open interfaces that allow us to assess that technology or that subsystem's contribution to the broader system.
Okay, any quick retorts, Jeff or Drake or Heather? Because unfortunately, we've come to the end of our time frame right now. And I really would like to thank you first, Heather, and Brian for doing a great job on the paper. And then Mr. Tremper and Drake and Jeff for joining us today to discuss Heather's report. So from all of us here today at Mitchell Institute, have a great aerospace power kind of day.